for me, much like I made those lists of the kinematic equations so that I could have them around, this is a nice set of forces, these forces that are described here, to put on a 3x5 card so that you can address a problem that comes up. Okay, most of them are going to be pretty straightforward. Now, they can get to be tricky, but let's look at one example. Matter of fact, I'm going to leave those up so we can see what's there, and then I can just draw on this board here. Okay, let's say I have an object that's sitting on a table like this. And I'm going to take a rope and I'm going to put a little pulley here. It comes and it's hanging on some mass that's here. Let's call this a 10 kilogram force, mass. Now, that 10 kilogram mass is what's going to cause the force to pull that box in that direction. Let's say this is a 20 kilogram mass. And it's sitting on this table. So the first thing we have to do is understand where are all the forces that are acting on all of these characters. First of all, we know that this has got a weight. It's sitting in the world. And so this is going to have a weight. Okay? That weight is equal to the mass times the gravity. So we know gravity is roughly 10, and that's 10 kilograms. So this is going to be 100 newtons. And especially these kinds of problems, I'm going to make some of those assumptions that gravity is not 9.8, but is in 10. So that's a 100 Newton force pulling this down. And that's also going to be the tension on this rope. Tension always just comes from what's on the other side of the rope, and it provides a pull in this direction of 100 newtons because it's equal to whatever's on that side. Now this object has got a weight. I'll call it weight 2. Okay, but that's 20 kilograms, and it's mass times gravity, so 20 times 10, that gravity, is going to be equal to 200 newtons. Okay? You know what I know is if I put some box on the ground, it's going to give a little bit of resistance because it's not a super slippery surface. And so that's going to be some force of friction. Okay? So you're going to have some sort of force of friction this way. I'll use that crazy looking U. It's the letter mu from Greek. But that's the coefficient of friction. Okay? So the coefficient of friction. Now, there's one last force on here because that mass that's sitting on the table isn't sinking into the table. And so there is a normal force. That's pushing on that mass. And what we're doing is we're saying every problem that we have that we want to see how something moves, we're going to show all the forces acting on it. This one's hanging there, so it's only the weight. Well, that's not true because there's a tension here. Okay, there's that tension. Tension is uniform throughout the rope, so as long as this isn't accelerating, we should be okay. That it's just the tension. Tension is the tension from the weight here. Okay? This mass is sitting on the table weighing 200 newtons. The table's pushing up, and that's going to equal 200 newtons. We already saw that the force of friction is the 200 newtons times whatever fraction that stickiness of the table is. Let's say it's always 1/2. It takes 1/2 the amount of force to pull it as it does to drag it. So I'm going to take 200, this is going to then be equal to the coefficient of friction times the normal force, which is 1/2 of 200. Let me go off the board there. Come back a little bit. So I've got this force, it's 100. We know this force is 200. We know the weight, it's 200. We know the tension, it's 100. Okay? So we could sit down to summarize all these forces, and that's where this is really the statement of Newton's second law. The sum of all forces, that's what that Greek letter, it looks like a sawtooth, it's a sigma, it's the Greek letter sigma. The sum of all forces is equal to this mass of that system and how much it will accelerate. Okay? So all of these forces that are acting in a certain direction, okay, Just like what we did in acceleration for free fall. If they're going up and down, that's one system. If it's going left and right, that's a different system. Okay, so we'll go all in the direction that this motion. Now, it looks like it's in the Y, but since it's all on a rope, it's all going to be moved in one direction. We'll call that same motion. Okay, so everything's basically moving in this direction, left and right. So what are all our left and right forces, including these weights? So I'm going to start from over here, and I'm just going to name them their originals, and then we'll put the numbers in. So you have the force of friction. I need a pen that you can read here, sorry. Force of friction, that's in the negative direction because it's going this way. Okay, you've got the tension, so that's in a positive direction. We know that the tension's here. Okay, it's pulling down this weight. We can say that's equal to the weight. And that's going to have to be, that's everything that's moving in this direction. Is going to have to equal the mass of this whole system, which is 10 kilograms and 20 kilograms. So that's 30 kilograms. And if that body is accelerating, you're going to be able to accelerate that. So let's finish this off. We know some of these numbers. Okay, you know that the mu, the frictional force here, is 200 newtons. Oh, times a half, so that's only 100. Okay, we know the tension is equal to the weight. This is a minus. Now, the weight is this way. This is what we said positive. This is what we're going to say is negative. So that's plus the tension, which is going to be 100 newtons. It's got to equal 30 kilograms times the acceleration. Now, I hope you've noticed already that this mass, is there still enough friction that there's going to keep this from moving, or is it going to move? Well, the force of friction is provided 100 newtons. The force of this mass falling down is 100 newtons. Those two cancel out to have no force. That's no net force, so that that whole system of those two masses is going to have an acceleration of also 0. So the acceleration in this case is going to be equal to 0. Okay, if that was greater, if we would have chosen a bigger mass at the bottom, we would have figured out what the acceleration was. Once we know the acceleration, we can even calculate how far this might fall or some other question. We always have to get the acceleration, then we can move back to the motion equation. So that's how these force problems are done.